السلام عليكم ورحمة الله وبركاته. محاضرتنا اليوم هي Power System Stability Part 2 إلى طلاب الجامعة التكنولوجية قسم هندسة الكهروميكانيكية. يلقيها على مسامعكم الدكتور غسان عبد الحسين بلال. Let's first define the transient stability. So the transient stability is the ability of the system to maintain synchronous operation and to reach stable states or the ones closed after a large disturbance. يعني من يصير عندنا اضطراب عالي بالمنظومة نحاول أن نحافظ to maintain synchronous operation على مود الوصول إلى stable state. So let's see the specification assumption of the study of transient stability. So we have 5 of this assumption, which are system resistance may be neglected in comparison with reactances. So the machine has cylindrical rotor, which is XC equal XQ. The system may be reduced to equivalent to machine system. Okay, and each machine may be assumed to supply an infinite path. Director X transient reactance XD is used for machine representation. So the problem of stability revolves around the determination of whether or not the torque angle, which is delta, which represents as a torque angle, will stabilize after a sudden disturbance. يعني أن يصير عندي اضطراب بالمنظومة إن نحافظ على التورك angle نكون be stable. Okay, in case delta continues to increase إذا استمرت التورك angle بزيادة after this disturbance the machine will lose synchronous. يعني generator or motor is going to be lose the synchronous تزامن مالته. Okay, so mechanics of angles motions. So let's see the swing equation. We're going to define the swing equation and we're going to see how we are going to get the equation in math. Okay, so we're going to derive this equation to get it in math. So the swing equation, which is the behavior of a synchronous machine, where during transient state, okay, is described by swing equation. So the behavior of a synchronous machine during the transit. So let's ask theta to be, what does it mean? Theta is the angular position. So the angular position, that means the theta of the rotor at any time. So which is going to be changing with the time. So the theta is going to be changing with the time. It's convenient to measure theta with respect to reference axis that are rotating at synchronous speed عندما يدور بالسرعة التزامنية. So the delta is the angular displacement الإزاحة الزاوية of the rotor in electrical degree شنو الدرجة الكهربائية from the synchronously rotating reference axis, while WS is the synchronous speed. So the delta is the angular displacement and the WS is the synchronous speed, which is 2 by F. Okay, so you have the formula, which is the theta, which is the angular position, equal synchronous speed multiplied by time plus the delta, which is the angular displacement. So we have this formula. We're gonna derive this formula, first derivative. So it's gonna be d theta over d time with respect to the time, and the time is gonna be go, and then just this is the constant and plus d delta over d time. So this is the first derivative. We're gonna this formula second derivative. So this is constant. We're gonna neglect it, and this is for second. So you will get this formula, which is what represent the angular acceleration تعجيل الزاوية, which we can call it alpha. So this is the angular acceleration, which is alpha. Okay, with this formula. So the motion of synchronous generator or rotor is determined by Newton's second law, قانون نيوتن الثاني, which is the moment of inertia, which is J represent the moment of inertia, and the alpha is the angular acceleration equal the torque, acceleration torque. So the acceleration torque, what equal the angular acceleration زخم الزاوية تعجيل الزاوية multiply the moment of inertia زخم الزاوية. Okay. So when the damping is neglected, we neglected, the acceleration torque in a synchronous generator is given by this, which is the mechanical torque minus the electrical torque. So this is represent the mechanical torque or shaft torque, and this represent electrical or electromagnetic torque. Both of them we can measure it by Newton meter. Okay, so we have some notes. So we're gonna see from this equation. So if torque, mechanical torque, larger than the electrical torque, that means you will get the acceleration torque in positive, which is right. If both of them they are equal, that means the acceleration torque is 0, and then you will get this, the rotor speed equals synchronous speed. So if mechanical torque less than electrical torque, that means is decreasing, because you will get the acceleration torque in negative. Okay, so the rotor is going to be decreasing. If both of them are positive, so for generator operation, okay, so this is 4 notes. Keep in your mind as apply all this formula. So now we have, this is the acceleration torque equal mechanical torque minus electrical torque. I multiply this equation with the Ws, which is synchronous speed, so you will get this formula. Okay, so this formula, so synchronous speed multiplied by the torque, it may represent the power, acceleration power. For this one is mechanical power, and this is for electrical power. So the mechanical power is mean the input power, and electrical power is the output power, or we can equivalent with this. So acceleration power is equal mechanical power minus electrical power. So you see from this equation we get this equation. Okay, by multiply omega s, and you will see this, and then from this this part is represent power, and you will get this. So now we return for this formula, which is the moment of inertia multiplied by the angular acceleration, which is the alpha, so angular acceleration. Okay, so multiply by moment of inertia, you will get the acceleration torque. So we have this, which is represent the second derivative of the angular position, and the same second derivative for the angular displacement. So which is, you will get the equivalent of this equation or this equation. I multiply this equation with omega s, what we gonna get? We're gonna get ws multiplied by j multiplied by second derivative of the angular displacement equal ta, which is acceleration torque multiplied by omega s. So you will get this equation. So this is represent what? Moment, and this is and this is represent acceleration power. So this, the equation was called swing equation. So we know the definition of swing equation is, what does it mean? Is the behavior of synchronous machine during the transit state. The equation is what is the moment, angular moment, which is m, multiplied by second derivative of angular displacement equal acceleration power, which is represent the mechanical power minus electrical power. Okay, and it's the relationship between the acceleration power and the angular acceleration, which is nonlinear differential equation of the second order. So now let's define m and h constant. The m, which is the angular moment, and we can measured by joule second over radian, and j is the moment of inertia, which is equal mr square. M, which is the mass of rotor, and r is the radius of the rotor. Okay, so now it's the kinetic energy of the rotor, which is half of moment of inertia multiplied by synchronous speed square. Okay, so you have moments, angular moment, which is equal moment of inertia multiplied by synchronous speed. And how to get this equation? So this is omega is half j omega s multiplied by omega s. We just separate the omega square is 2 omega. So this is represented as m, right? Which is this one. So 2 multiplied by omega. So you're gonna multiply this here. So you will get 2 omega, and this is m omega s. So now if you want m, which is dou w, kinetic energy, 2 multiplied by kinetic energy of the rotor over synchronous speed. Okay, for this one, which is the torque equal the moment of inertia multiplied by angular acceleration, so the power is equal omega t. We know this, and the t is the j. We substitute this by the t, by the torque, you will get this equation, and j omega, which is represent the moment, and you get m alpha. So the m equal the power of angular acceleration, which is the Sahn Zawi. Okay, so we have a second formula of m. So you can use this for the m, depend about the given in the questions. So while for the h constant is called the inertia constant, which is the ratio between the kinetic energy in megajoule at the synchronous speed of the machine rating in mega or volt ampere, which is W over S. So the W kinetic energy, if you see from this equation, which is what to represent, if we get the W, which is what is M omega S over 2, right? So we can substitute it here. So omega S m over 2. This is to represent as what? As a W, kinetic energy, over S, which is this S. Okay, so you will get this. So omega S, what does it mean? Is 2 by F. So we substitute instead this 2 by F. So this is 2 by F, this is the M, and this is 2S. So now we neglect the 2, so you will have pi F M over S. S is the rating, megavolt ampere. This is the moment, okay? And F is a frequency, and pi, you know. Now, if you want to get m, which is multiply sh, which is hs over pi f. So you will get this formula. So this is the third formula of the moment, which is we can measure it by moment joule over electrical radian, which is the same, but this is in 3.14 and this is 180. So this is in degree and this is in radian. So the same equation can be written as, but in actual value. We can get it in actual value by this is because this is in megavolt ampere, which is the same formula, but this is in actual. If you want it in per unit, you can divide it by S, so you will get this is in per units. So we can divide by S base, so you will get this is equation in degree and the same per unit, but in radian because this is 180 and this is 3.40. Now let's take example to see what does. So first example, 50 Hz 4 volt turbo generator rated as we have S mega and 11 kilovolt has an inertia constant of 8 megajoule for over megavolt ampere. Find the energy source in a rotor at the synchronous speed, and if the machine input is suddenly raised to 80 megavolt and electrical power is 50, so find the rotor acceleration, neglect mechanical and electrical losses. So the first we have the W equal SH from the formula. If you go to the formula, we will see we have this omega is SH. So S is the 100 megavolt ampere, which is the rating, and the H is the constant, inertial constant, which is 8. Multiplied by them, you will get the storage energy. So we have an acceleration power, which is we have uh, 80 and 50. This is the input, this is the output. Subtract them, you will get the 30 megawatt, which is the acceleration power. And from the same equation, we have H S180F, second derivative of the angular displacement equal the acceleration power. So we have 30 here, and we have S is 100, and H is 8, and F is 50. So we substitute, we'll get the acceleration displacement, which is the second acceleration displacement, which is the same angular displacement, angular moment, which is Zahn Zawi. Okay, so this is the what this is in actual. Okay, because we use the 100. If you want it in per unit, we just divide on the base of this. You will get in per unit. So the H constant on a common base. So we have inertial constant. We have this formula. It represents S system equal H machine over S machine for S system. So we can use this formula in order to calculate the H system. So the equivalent system, suppose that the number of generators are connected. If we have number of generator, 3, 4 generator in parallel, connected in parallel at the same bus bar, we can use this formula, which is the energy stored by equivalent machine equal sum of energies stored by individual machine, which is as you see this. The V equivalent equal W1, W until Wn. So for S equivalent, H equivalent, H1, S1, S2, S2, on, so on so far. And for S equivalent, which is the same, S equivalent is equal S base, and you have this is the final formula that you can use when you need to calculate the number of generators connected in parallel at the same bus bar, which is H equivalent equal H1 over S1 space plus H2 and so on and so forth. Let's take two examples to see what this means. A 2-pole 50 Hz 60 megavolt turbo generator has a moment of inertia. This is the value. Calculate the kinetic energy in megajoule at rated speed. So this is the formula of kinetic energy. So the moment of inertia joule, we have it. So 9 by 10 up 3, and omega is synchronous speed up 2. So you can calculate the synchronous speed by using this formula, or you can use it by 2f. F we have 50 hertz, so you will get this is the value which is the same, this value, okay, which is the same. Two-way is the same, you will get it. So so now we have a moment of inertia and we have omega s, and then you will get this value. Okay, so omega second calculation with the inertia constant m and h equal sh. So we have a rated s which is 16, and we have a kinetic energy. You can get h for m is w over 180. So this is for electrical degree. So we have a kinetic energy over 180 f, which is 50 hertz. So we will get m. So the second example, we have 500 megavolt synchronous machine has H1 and 150 megavolt and H2, and this is the two machine operate in parallel in power station. So what is the H equivalent? We have the formula, and the base is 100 megavolts. So we have this equation as you told you. For this equation for the equivalent, we can apply it. So we have H1 for the first one, which is 4.6, and we have S1 500. Okay, so for the second one we have 3 and 150 100, and then the base is 100. Okay, so this, I hope you get this is the lecture, and please if you have any question let me know. Thank you so much.